Hey everyone, I'm quite excited to be sharing with you today a tutorial on how to interact with a Redshift database through Amazon via the use of JupiSQL. In this tutorial, I'm going to work with you to establish access to a hosted Redshift database instance. We're going to go ahead and create some tables and populate those tables with data from S3 buckets. And then from here, we're going to be working within the Jupyter environment to work along with JupiSQL to perform SQL queries against the database and perform some exploratory data analysis. Really, the key here is we're going to be bearing most of the work with SQL and JupiSQL in the form of creating the tables, populating them, merging tables, and doing data cleanup. And then from here, we're going to take a look at how, via things like the PyProject TOML, we can automatically transform the content of our queries into pandas data frame format for visualization and modeling with scikit-learn. So JupiSQL is an open source project that has as a main goal to allow users to enable to run SQL queries within the Jupyter environment via the use of magics. Some of these magics can be identified by the percentage sign and double percentage sign, and they include magics like SQL, SQL plot, and SQL CMD. It is compatible with all major databases, data warehouses, and embedded engines, and the community is constantly looking for ways to upgrade the current databases that it is compatible with. With Amazon Redshift, we can use SQL to analyze both structured and semi-structured data across a number of different platforms, including data warehouses, operational database, and data lakes, with AWS designed hardware at the core of it. In this particular video, we're going to be pulling data from 3 different sources, creating tables, and merging them through the use of SQL commands. And I'm going to be basing this tutorial on an example that was created under AWS samples repository, but I'm going to modify a few things. One of the things that I noticed about this tutorial is, I'm going to go ahead and show you. So they'll typically start by setting up the user endpoint for the Redshift cluster. They process to grant privilege to the IAM role user. And then to perform SQL queries, they have this function called run SQL that takes as input some text. Part of what's going to be given to this run SQL function is the following data preparation script, which is a pretty large script to generate some of this data, populate the tables, and do some data cleaning and data wrangling. So my goal with using JupiSQL is going to be to add more interactivity and break this down into simpler steps that I can verify as I do them. The other thing is I want to remove the need to execute scripts outside of Jupyter. When setting up tables, I want to make sure that I test things and I verify them as quickly as possible. And I want to also have the ability to automatically convert SQL query results to pandas or polars data frames for further analysis. If you're curious to see further documentation on how the model was built or some of the data sources that are picked, feel free to visit either the GitHub AWS samples Getting Started with Amazon Redshift Data API or through their blogs on machine learning where they build regression models with Amazon Redshift. So some of the prerequisites that we're going to be needing include, of course, an AWS Redshift username and password. You're going to need to set up a host. It'll be good to have S3 buckets with data. In this case, you don't have to have one from scratch. We're going to be following the one from the tutorial. And of course, Jupyter Notebooks and the JupiSQL extension. This is worth noting. You can actually run all of these analysis in your local computer. You don't need to purchase any more units or set up a SageMaker instance just to run these notebooks. You can actually just do this locally via JupiSQL. Okay, so we're going to go ahead and set up access to the data, the databases, and the tables. So the first thing we're going to be working with is installing JupiSQL, as well as SQL Alchemy Redshift and Redshift Connector. We're going to be using the pip module to go ahead and install this. And then from here, my goal is to import a few key modules. Now, one of the things that I'm going to be working with is loading my credentials securely. So for that, I'm going to be working with .env. I'm also going to be using 2 features from SQL Alchemy, Create Engine and the URL. This will help us build the URL for our Redshift instance, as well as set up the URL for our engine to be used. Now, for the credentials, one of the things that I'm doing is I create a .env file that has the following form. It'll be initialized by a parameter or variable names. that are set equal to a value. In this case, if you create a .env file, make sure that you populate it with your username, your password, your host information, and the IAM role. In this case, you will probably need to have a Redshift space associated to it and your account ID. Now, once I've done this, I can go ahead and load the .env file within my Jupyter environment via the load.env function, where I can now access the variables that correspond to this .env file. From here, we can go ahead and form the connection string. We're going to be working with Redshift and Redshift connector. We're going to pass our user, password, the host, and we're going to go ahead and create an engine. And this keyword here, engine, is going to allow us to initialize the GPSQL extension that will essentially establish a direct connection between our Jupyter notebooks and the database. So from here, I go ahead and load or reload the extension. So I typically go via reload extension SQL, and then it'll say again, found by Project TOML, and settings changed. So these settings allow me to change the default behavior of GPSQL when it comes to interacting with databases. One of the features that I have set to true is this auto pandas feature, which will automatically convert any SQL query output into pandas format for me to continue working with it. From here, I can go ahead and initialize access to a Redshift instance via the alias Redshift. Remember, this engine was built with the URL via the connection string. So in this case, all I have to do to bring access to my SQL engine is go SQL engine and give it an alias. And then from here, I can go ahead and start creating tables. Now, part of the key thing about involving GPSQL is that we can enable more interactivity in the process. So instead of running a single script that runs all the tables and hope that everything works okay, we can break it down into simpler chunks and test that each of those chunks work appropriately. So one of the things that we can do, for instance, is start creating tables from S3 buckets. We're going to be creating 3 tables. We're going to be creating a table on ridership information. This contains information on bike sharing rides taken between 2017 and 2018 at the City of Toronto. And data on this is taken from an S3 bucket. Notice that with GPSQL, one of the things that we can do is we can parameterize our queries. So I can continue to pass the IAM role parameter as one of the parameters through the notation quotation marks, double brackets, followed by the variable IAM role. Remember, we initialized this when we read the variables from the .env file. And then from here, we can populate the table that we just created that'll contain the ID, the duration, the start time, stop time, with the information from the S3 bucket. We can then verify that everything worked okay. So one of the magics that we can work with using GPSQL is a SQL CMD magic that allows us to visualize and take a look at some of the information contained in our table. So in this case, notice we gave our table the name ridership. So if I go verify here, I can go ahead and check that the columns were created appropriately. And I can furthermore do a quick data profiling to make sure that the number of records looks okay, that the mean is looking okay, etc. So it's really enabling more interactivity in the process. We're going to go ahead and do something very similar with a weather table. We're going to go ahead and extract this from an S3 bucket via the IAM role. And we're going to pass information pertaining to the weather station via the longitude, latitude, the station name, the climate ID, etc. For this particular problem, we're going to be focused on extracting the temperature as well as the precipitation amount in millimeters. So later, in a later stage of this video, we're going to do a little bit of data wrangling. And then from here, we can go ahead and verify that this worked okay. So we can use the SQL CMD magic, pass the columns option, followed by the flag T, followed by the table name, in this case is weather, to verify that the information was processed correctly. And then again, we can go ahead and do some data profiling. Now notice that in this case, because we're dealing with things like latitudes and longitudes, average statistics don't necessarily make sense, but we can still verify things like that the number of records is appropriate. The last table we're going to create before we move into data wrangling is holiday. So in this case, we want to extract information on holiday dates for a given time range. And in this case, we only have a single two columns, a holiday date and a description. Again, we extract this from an S3 bucket via the use of our IAM role. And again, once more, we can go ahead and verify that things were loaded correctly. Okay, so here's where we get to do a little bit of data wrangling. So the next thing we want to do is we want to start merging some of these tables so that we can perform analysis on what kinds of things are impacting whether people take rides on their bicycle or not. And of course, we want to take a look at whether the temperature is a factor, whether if the precipitation is a factor, and whether holidays or the day of the week are a factor. So to do some data cleanup, we're going to use SQL to transform the records so that they're all in local time. In this case, the data before July 2017 was in UTC versus the data after was in Toronto's local time. So we'll want to make a data conversion. We don't want to have trips with a duration of less than 60 seconds. We don't want to have trips that are longer than a day. And then we also want to aggregate the data on an hourly basis. Finally, we're going to break down the trip date into column, day, month, year, quarter, month, weekday, and month, week to make sure that we can start evaluating some correlations between the number of rides and some of the parameters. So we can go ahead and do something like this with SQL via the create or replace view command. In this case, we're going to create two views. We're going to create a ridership view and a weather view. And for the ridership view, as I mentioned before, first we're going to go ahead and make sure that we're processing any dates that are less than 2017 July 1st and convert them to UST Eastern Time. We're going to go ahead and remove all of those trips that are less than 60 seconds or more than a day. And we're going to go ahead and store the content of this wrangling into the ridership view. The last thing we're going to do is to create the weather view before we do the final merge. In this case, our goal is to transform the records from UTC to US Eastern Time Zone. We're going to aggregate the data to an hourly basis for better generalization. And then things like visibility, kilometers, and wind chill are empty. We're only, as I mentioned, we're only going to be working with things like the temperature and the precipitation amount for our model. So in this case, we can go ahead and use SQL to create or replace the view and perform the desired operations. And then from here, we can go ahead and verify both tables. So remember, we had our weather view and our ridership view. So here is our weather view. So I can verify that both of them were created correctly. And then I can do some data profiling to make sure that everything is working okay. Okay, so here's where the merging comes in. So we have a ridership view table, we have a weather view table, and then our goal is going to be to go ahead and merge these tables to make sure that we have it all in one place. So in this case, we're going to keep the trip time, the count, the hour, the day, month, year, quarter, month, week, weekday from the ridership view table. And then we're going to go ahead and grab the temperature and precipitation amount in millimeters from the weather view table. In this case, we're going to do a little bit more processing. We want to encode the holidays as 1 and the non-holiday days as 0. And then from here, we're going to go ahead and join our tables where via the use of trip time in the ridership view is equal to the daytime in the weather view. Okay, so we can go ahead and verify that this worked. So in this case, the total count of records after doing these operations are 17,306. And we can verify that our information is looking good. NANs for things like trip time make sense. In this case, it might be due to how, in this case, it's due to the fact that the trip time is encoded as a timestamp. So it doesn't make sense to take things like statistic averages, but I can go ahead and process pretty much everything else. Things like temperature C and precipitation amount, these might be encoded as numeric. So we might have to do a little bit of data cleanup for those, but we are ready to start visualizing and exploring. So from here, my next goal is to use this data to perform data analysis and set up an initial model. In this case, we're going to go ahead and visualize and wrangle our data. I'm going to be using Seaborn as well as Matplotlib. And then one thing that I want to bring back, if you have forgotten, is the use of this extension. Remember that one of the things that we can do is control the default behavior of GPSQL. So you can easily change whether you want your query results to be formatted in pandas or polars format. I'm going to be working with pandas in this case, so I've set auto pandas equal to true. And then from here, I can go ahead and select every column from the rounded trips table. That is a table that contains a merged ridership view and weather view. And I'm going to add an extra column called rounded trips. So this just rounds the total number of trips divided by 100. So once I go ahead and make this query, you'll see that the result is automatically parsed in pandas data frame format. So here again comes the SQL magic. So one key difference between the double percentage and single percentage is double percentage will transform the entire cell into SQL syntax, versus with single percentage, I can mix Python and SQL. So this line will allow me to set this variable to, the result of this SQL query into a variable called result, which I can then process using Python format. So in this case, I can do things like info, if I wanted to do result.info, or describe. So now we see that result is of type pandas data frame. Okay, so the next thing we want to do is some exploratory data analysis. So first we want to take a look at the distribution of number of trips, and we see that if we're working with the trip count itself, a lot of the times there weren't any trips, and it's very rare that in a given day we have more than 200 trips or more than 400 trips. So we're going to go ahead and create a little bit of a categorical variable soon, where we have trips or days, where there were less than 200 trips, or days where there were more than 200 trips. If I go ahead and take a look at the rounded ones, we sort of see that there's a big dip in terms of days that had a higher number of trips. If I want to take a look on the distribution of trips, based on whether it was a holiday or not, we see that most trips are taking place on non-holiday days as opposed to holiday days. So that'll be interesting to see how it impacts the model. And then, of course, we want to take a look at whether the temperature and the precipitation is impacting whether people want to go and take a bike ride. So we do see that on days where the temperature was quite low, we had a much lower number of trips. In this case, I'm using the rounded one so that we don't have as much noise. And then on days where the temperature is higher, we do see that there's the number of trips on a given day was indeed higher. If I take a look at the precipitation amount, we sort of have the opposite thing happening, where on days where there wasn't any precipitation, we had days that had a higher trip count. And then on days where there was a lot of precipitation, there weren't as many trips. So we can start thinking in terms of how to build our model. Okay, so I'm going to go ahead and create a binary column called load trip count to account for days in which there were less than 200 trips or more than 200 trips. And then my goal is going to be to classify whether certain days will have less than 200 trips or more than 200 trips. Some of the prerequisites. So I'm going to be working with scikit-learn, and then I'm also going to be working with scikit-learn evaluation. This is a package developed by the Plumer team, which is also the team behind GPSQL. And the goal is to make the process of evaluating results and plotting things a little bit easier. In this case, I'm going to be working with a random forest classifier from the scikit-learn.ensemble module. I'm going to be, splitting splitting my data into training and test. And then to evaluate, I'm going to be working with the accuracy score, the confusion matrix, and the classification report. So from here, the next thing I want to do is to set up my load trip count column, where if the total number of trips is less than 200, I'm going to give that a true and a false otherwise. And then for starters, I'm going to be working with things like the trip hour, the trip day, the trip month, trip year, the trip month week, the trip weekday, the temperature, the precipitation, and whether it is a holiday or not as my dependent variables. And then my target variable is going to be that load trip count. So I want to predict either it's a false or a true. From here, I go ahead and split my data into training and testing. And then from here, I can go ahead and initialize my model. In this case, I have split my data into training and testing. I can make a prediction. And then from here, I can evaluate. So based off of the testing information that the model was given to assess its accuracy, we have an accuracy of 0.94 with precision recall and FWS score of above 90% for both the true and false categories. And then from in terms of evaluating where things are going wrong, we're seeing where we have about 85 areas that were misclassified for the class false and 97 that were misclassified for the class true. Similarly, if we want to take a look at what are some of the factors that are most important when it comes to predicting whether a given day will have a high number of trips or a lower number of trips, we take a look at the trip hour, the temperature, the month, the day, and the weekday. This would make sense, if people are typically tend to go out riding their bike in the evening as opposed to in the morning. This might be something to take a look at. We saw that temperature was definitely impacting whether people were eager to go out or not. And then for the month, it would make sense that if it might be trickier to go biking on the colder months where it's raining or snowing as opposed to the warmer months. Okay, so for the key takeaways, so we use the Jupyter Notebook extension JupySQL to enable access to Redshift instance. We followed this AWS samples tutorial, but we gave it a bit of a spin. Instead of executing a huge script via the use of a Python function, we leveraged SQL to perform those queries directly and do a little bit more of an iterative approach where we focused on doing one table at a time and then testing that everything looks good. The advantage of this is, of course, that we have that feedback immediately. Furthermore, we were able to customize the default behavior to be of format pandas, and we can change that to be polars if you prefer. And then from here, one of the things that you saw is that I was able to use JupySQL not just to create those queries, but also to parameterize them and extract data from an S3 bucket. From here, we do the classic data science workflow where we perform our data cleanup. In this case, the data cleanup was mostly done through the SQL commands when we did cleaning up the dates and merging the tables. But then we were focused on mostly using the visualization and modeling with scikit-learn once we had our query results in pandas format. If you like JupySQL and if you'd like to learn more about us, you can find us on github.com/plumer/JupySQL. And remember that this is a pip-friendly package, so you can also install JupySQL via the pip command. So I hope you found this tutorial useful, and I look forward to the next round.